Myself, JV, and Dr. Kiran Yadav. In this session, I will discuss about specific heat or heat capacity of solids. So let's start our discussion. So let's start with the introduction. It is always important to study the condensed matter. There is another example that classical kinetic theory cannot provide answers that agree with experimental observations. Dulong and Pettit observed in 1819 that the specific heat capacity at constant volume of all elementary solids is approximately 2.49 into 10 is to power 4 joule kilomole inverse Kelvin inverse, that is 3R. Dulong and Pettit's result can be explained by the principle of equipartition of energy by treating every atom of the solid as a linear oscillator with 6 degrees of freedom. Extensive studies show that the specific heat capacity of solid varies with temperature becomes zero as the temperature approaches zero. Specific heat capacities of certain substances such as boron, carbon, and silicon are found to be much smaller than 3R at room temperature. The discrepancy between experimental results and theoretical predictions leads to the development of new theory. So the new theory is Einstein's theory of the heat capacity of a solid. The crystal lattice structure is of solid comprising n atoms that can be treated as an assembly of 3 indistinguishable one-dimensional oscillators. The assumption is based on that each atom is free to move in 3 dimensions. The internal energy for n linear oscillators can be written by this equation. So on calculating the internal energy for solids, the formula for U comes out to be as shown in the slide. Here theta is the Einstein temperature and can be replaced by theta E. And this is the formula for heat capacity, which is just the partial derivative of internal energy U with respect to time. So on applying the limit when T is very greater than theta E, we can consider the term theta upon T as less than equal to 1. So E is to power theta by 2 will approach to 1. So using this we calculate the value of CV, which comes out to be 3 Nk, and this result is the same as Dulong and Pettit's law. Case 2 is when T is much less than theta E. In this case, the ratio theta by T is very greater than 1. So in this case, the value of CV is as shown in the slide. As discussed earlier, the increase of theta by T is outpowered by the increase of E to power theta by T. As a result, when T tends to 0, CV tends to 0. If an element has large theta E, the ratio theta by T will be large even for temperature well above absolute zero. When theta by T is large, CV is small. Since theta E is equals to h nu by k, a large theta E value means a bigger nu. On the other hand, nu is equals to 1 by 2 pi square root k by u. To achieve a larger nu, we need a large k or a small u, which corresponds to lighter elements and elements that produce very hard crystal. So this was all about specific heats of solids. Thank you so much.